You know what we call a connected component. Classical. What is a connected component? Here, for example, can we consider that as a unit, a connected component? When you look at an aerial photograph like that, you see some places which are called villages. They are not called isolated houses separated. No, they're called one thing, a village. So though they are disconnected, they appear as one object, a single object. So you should try, or we will try to define an approach which allows to say that this is only one thing, one connected component in some sense, which is not the classical one. Here is the contrary. If you take, it is a ball of cotton. If you take the set of all these balls, they are totally white and totally connected. But by segmenting, you will separate some zones. So starting from an object which is connected globally, we are interested indeed in some subpart of it that we will call connected components. So in these two examples, you have either more than the elementary units or less than the whole scene that you see. Now, in math, the connectivity is a topological notion. You start from a topological space, and you say that the set is connected when you cannot cut it into two parts which are closed, both, or open. Okay. We can criticize that because we don't need topology. We are working on sets without any topology, and it is really tortuous for what we want. But there is a basic theorem which states that when you have several connected components which have an intersection, then the union, which are non-empty intersection, then the union of this component is still a connected component. When you have a family of connected sets whose intersection is not empty, the union is connected. So that is a consequence of the topological definition. And as this topological definition was particularly difficult to handle, they have given another definition in math, which is the one which appears in image processing, which is the connected components by arc. What is by arc? An arc is an image of the segments O1 in the 2D space, for example, and the set is connected when each pair of points can be associated with the extremities of an arc, which is totally included in the set. This definition is more restrictive, but when you consider, or again, with the topological approach, the open set of the Euclidean space, the two definitions are the same. The general one and the one with the arcs. But what we have to keep in mind is that what happens if we drop completely the topological background and we start from this condition as an axiom? We will say that we will consider that a set is connected when E satisfies that. So it will not be one set to be connected, but a family of connected sets. It's such that when you take the intersection of two or more elements, and this intersection is not empty, then the union is still connected, belong to the same family. So there is in image processing a double approach. You can consider the path or the arc. The arc is a path in digital space going from one point to another, and that gives you a certain definition of the arcwise connectivity. But you have something else. Very often, you have a marker. You have a set, you say, I want to be interested in the connected component which hits this point or which is inside a certain marker. So you approach by intersecting by something else, and you want to extract the connected component. In this sense, a particle, or particle is a word for connected component in image processing, is something that we want to pick out from up a point considered as a marker of a particle. And the idea here is that if you take another point, it can take the same particle as the first one, or another which is totally separated. So you have a certain segmentation of the space by the connection. So we do not want the topological background because it is basically useless, and we want to be able to find or to characterize this approach when we want to pick the good particles according to some marker. So we will enter the problem in the following way. We call a connection a series of sets, a family of sets, in a space which is totally arbitrary, such that the points are considered as connected, and the relation we saw before, when you have a family in this class, that is the class of the connected sets, a family in this class such that the intersection is not empty, then the union belongs to the class. So a class of connected sets is called here a connection. Connection is a family of all the connected sets. And the elements are said connected components, or said to be connected. It's easy to see that the topological and Aquarius connectivities satisfy that and satisfy that. So they are particular case of this definition of a connection. So now the second point of view that we indicated before, it appears immediately here. When you have a point, you can consider all the connected components. You have a point and a set. You study a set. You put a point and you can consider all the connected components of your family of connection, which are containing this point and containing the set. So there is a union of that, which is still a connected component by the axiom we had before, and which is the largest one because you cannot, you take all of them. So then you have what we call an opening, which means that we have selected part of the initial set, we have less than the initial set. If we repeat the operation, the result will not be changed because we got the connected component. If you start from this connected component and you take again the same procedure, you get the same. And if you have a set which is smaller, the connected component is smaller. Moreover, we have here three more properties. If the marker at point x is applied to the set which is the point x itself, then you get it. If you take 2 points which are different but act on the same set, you will have either the same opening, the same gamma, or 2 gamma which are disjoint. And finally, if you take a point outside the set, you will find no connected component, so it will be the empty set. And that, when you take these two axioms with that definition, you have exactly a connection that can be proved. So the connection is equivalent to this operation, which is the way by which we act on the connection, plus these three constraints. So every connection induces a unique family of that, and the result of this operation, which are invariant sets for the operation, are the element of the connection. And it works in both senses. So In digital imagery, a connected component may have several sense. If you have practiced already, you know that you have in the plane the 4 connectivity, 8 connectivity. They are all path connectivity, but different. You accept the diagonal or you refuse the diagonal. And in the space, it's more complex. In the 3D space, you may define a number of connectivity, 7 or 8, starting from the cube. Now, we will see other examples which cover the 2 situations which were in the photograph initially. A cluster of elements, small houses, for example, and a division of the space. The clustering connection, so it's a bit abstract, but when you have a dilation, each point is replaced by a disk, and you take the union of all the disks, each point taken initially in a set, so you dilate the set, and you see what are the classes which appear. I'll show by an example. Here's that. You see intuitively that here you have a sort of cluster, you also. How to define that? Each point is replaced by a disk, and you take the union of the disk. Each point of the grid, the union of all these disks gives you that. And now you consider the connected component in the normal sense, in the classical sense, an arcwise connected component, for example, of the dilates, and you take what falls inside, what are the grays inside each connected component of the white. And that defines a second connection, a second level connection, if you want, where all these points are considered as connected, all these points are considered as connected, this one is not, this one are one connected component. So it's the village, if you want. It depends, of course, of the degree of what you decide to accept as a connected component. If you take a dilation which is larger, after a certain time you will reconnect sets with the others, or that one, and the feature will appear differently. That is a technique for separating the connected components. That is an example. That is the city of Nice, and we can be interested in the houses. Here we have all the houses, is the center of this, the old city, in the current city, the airport is over there. So we can see what are the neighbors of the houses, if they are close or not. So if a house has a large garden, it will be far away from the neighbors, and then it will appear as an isolate point in the previous approach we had for defining what is connected. So exactly what happens. So all that is one connected component. All that is one connected component after a certain size of dilation. This one is one connected component. This one also. All that is one connected component. And if you take the difference between this image and the initial image, you have all the houses which are separated from everything, which are isolated, probably because they have a large garden. You can, from the map, have an idea of the structure of the city. Another example. If you take a time sequence, you know that there is a discontinuity. The ping pong ball normally has a continuous motion, but in fact, what you see is that if you take the same space and you segment the ball because it's white, you see that is the time and that is the location. And it's a moment when the guy with the racket does that, and hop, the ball starts, describe the parabola, and again. Here again, you can perfectly represent reconnect all of these small spots and have a connection in the sense of the second level connection. But you can also, if you want, to measure the speed, for example, to see when they are connected by smaller dilation. And you see that at this moment the ball is very fast, so there is a large distance between two moments when it is taken by the camera. And here it's the contrary, it's one block, and here again they are separated. So you have that 1, 2, 3, 4, 5, 6, 7, 8, 9. So you see the speed, if you want, which appears. Another example of connection, which that is a toy example, but it appears in practice very often. It is the case of segmentation. You have an object, which is this one, and you have a certain marker, a certain division of the space, which is a partition which is given a priori, separately from the object, which is made by here, these lines. So that are the classes of the partition, this one, the triangle, this one, and so on. And we consider as one connected component all the green which are in each class of the partition. So for example, here, the connected component is the union of these two. Here, the connected component is also connected in the initial sense, is that. Here, the connected component, I don't know what the initial side. Here you have that, and so on. Here you see very well how it appears. So you split the initial connected component, and you regroup differently two things which were initially disconnected, but which belong to the same class. So it's the intersection between some partitioning of the space and a first connection. That appears very often in practice. It's let's say, a symbolic way to represent segmentation in image processing. So we speak of a lattice. We did not see what is a lattice. We will see next week. But clearly, a lattice is a structure where you have an ordering relation. You can say that an object is smaller than another, and whereas for any family of objects in the lattice, a greatest lower bound and a smallest upper bound. And here you have a lattice. The infimum, in particular, this is interesting for the infimum. The infimum of the lattice, I don't know why, it's just the intersection of the connection. If you want, when you have two connections, two families of connected classes according to a first criterion and a second criterion. If you take the elements which are in the two classes, which are therefore connected in the first sense and connected in the second sense, then they form also a connection to satisfy the property of being connected, having the pointwise opening and so on. The supremum is more complex. That also is interesting. When you have a connection and a set, the connection allows you to divide your set, to segment your set into classes which are the largest one you can imagine, satisfying the property of the connection. For example, we just saw before the segmentation by cutting with a partition by lines. What you obtain is the largest connection for each set, the largest connection, the largest classes for which fulfill the connection. It seems to be obvious. For example, when you look at a set, you see the particle. Yes, effectively, but it is important. They are the largest classes satisfying the largest classes of the set satisfying the connection rule. How to implement a point connected opening, the operation we saw previously to get a point and to have the connected component which is around. So we will use what we call geodesic metric. It is the following. That is a set. That is a point. And imagine that the set is made of water, yellow water. And from going from one point to another, you can only, you are a fish, you can only follow a path which is in the water, not outside. So you cannot go from X to Y by the straight line. You must go by a path which is in the water. And if the set is connected, and if it is connected and closed topologically, you have a smallest path. If it is connected and not closed, you have a smallest distance, but you cannot find a finite path. But anyway, you are always a connected, a minimal distance in a connected set. And if it is not connected, you say that the distance is infinite. The distance between this point and that point. You see also that when there is a minimal path, the minimal path is called a geodesic. It's a path which corresponds to the distance between the 2 points. The geodesic is not unique. You can go from one point to another by several paths. So it is a distance. So the distance included in the set is a distance. It is larger always than the distance, the Euclidean distance, or the path Y distance in the connected distance in the grid. And it is not unique. And it is obtained easily if you want to characterize now this particle from this point. It is obtained by dilation from this point. We will see now. It is exactly the waves, physically speaking, when you have a small pond, a small set of water, and you drop a stone, and you see the rings, the ondulation of the rings of the stone which fall. Exactly what happened here. You have initially the progression of the wave, which continues, and which indicates exactly the distance in the sense that we just have defined, the distance from this point to that point. That are the set of the geodesic from this point, or the set of the, not the geodesic are normal, the set of the frontier of the balls starting from this point. And how to get them now? It's very easy. Suppose that you are in a GTL space. You start from the elementary disk of size 1 around the point. You put it, and you intersect by the frontier of the yellow zone. On the results, again, you make a small dilation of size 1. You replace each point by the small ball of the radius 1, and you cut and so on. I don't know, no. Here you have an idea of how it happens. So you introduce a small dilation of size 1 by this symbol, and you intersect that by X. So your marker here is called Y. It can be a point or it can be more. You start from here. That is the sets you want to grasp. When you make this sort of dilation, you extend the zone of Y, and you cut each time by X. So finally, you progress only in the direction which are permitted inside the set X. If you iterate, that is, you take the dilate of Y intersected by X, the result is again dilated and intersected by X, and so on. There is one moment when you invade completely the set. And that's served to a certain number of things. For example, if you start from these markers and you do the operation we did just previously, you recover only the set which are marked, that is these three connected components, and you drop the others. That is called the reconstruction of mean. The marker gives you a subset, extract a subset of the initial set which was in red. And it is characterized by that. So that is a complement operation. So, an example. You start from an initial image and you want to find all the particles which have a certain radius, the maximal radius of the disk which is inscribable. So you make an erosion in the reverse sense of a certain type, for example 10, and you take all the disk of size smaller or equal to 10 that you could put in the particles. You obtain that. That is a marker, and from this marker you recover the particles which are marked by that. This one, for example, gives you this one, that gives you that one, and so on. So here you have all the particles whose inscribable disk is bigger than the cutoff we have taken, 10, I think, here. Another example. Extract the object which cuts the edge of the mask. When you have an image, you are always disturbed if you want to measure something, for example, like a length. You are disturbed by the edges of the zone under study because it can modify the measurement you want to do. If you want to measure the length of the dendrite, they are dendrite, metallic dendrites, you will not arrive, except if the dendrite is totally included in the object, in the mask. So what you do is to take as marker the border of the mask and to invade the object in white from this outside border, and then all these particles will be taken, and the only ones which are not accessible from the border are the ones which are totally included with their whole length inside the mask, and it's the one for which you can measure. So it's again the same type of procedure. Again, another one in the same style. How to fill holes when you have object with holes. Again, you consider the background, and now you work on the background and not the foreground. So the object, the set you study is the white. Again, you take the edges of the mask, or the part of the edge of the mask which falls inside the wall. This one, which is in the white. And from that part, the dark lines, you invade the white background. So you will invade all the points, except those which are not accessible, these ones, which are not taken. So after, the only accessible zone gives you the background of the transform image. In this transform image, since you could not access internal pores, there are no fill and regroup with the grains. The system works, except that the algorithm is not able to see if this is a hole or not. Indeed, maybe it is not. Maybe the particle continues here and there, so then it will be not a hole. Or maybe, probably, there is a hole here, but we are not sure. So it leaves it as it is. It's also the technique for separating the two steps of processing when you have a set. When you have a set, there are many processing that you can do directly on the set. You can measure, for example, the total length of the border. You can measure, I don't know, the total area, the number of pixels. But you can also be interested in separating successively the object and measure, for example, the size distribution of the areas for the first, the second, the third. So then you have to start from an algorithm which gives you recursively the various particles. And the idea is to take the scanning as a ordering of the image or of the space. As soon as you touch for the first time one particle, you have 1 point that you consider as a marker, and you don't consider the rest of the scanning. Here, from this point, you recover the particle. That is an intermediary step. You measure what you want in this particle. As soon as you have finished your measurement, you take the set difference, that is the point which are here but not there. The set difference gives you 2 new particles, and again, you apply the same processing. You write to the first point. The first point allows you to extract the particle, you measure what you want, and you reject after by taking the set difference. It is what it is written here, and it is a very classical technique for that it is a very fast system for measuring separately connected particles and starting from an object which is composite. Okay, so we stop for 5 minutes. Do you have questions?